constraint system, then finite and differential constraints. After that, we discussed about the holonomic and non-holonomic systems, the stationary constraints which does not involve the time component. Explicitly means if f is a constraint, then curly f by curly t is 0. After that, we discussed about I think the celeronomic and rheonomic constraints. Celeronomic constraint are those a celeronomic system is that one in which all the constraints are of type stationary, and when the constraints are dependent on time, then it is known as rheonomic system. Today we people are to discuss about possible displacement, virtual displacement, and possible velocity. To discuss it, first we are going to discuss an example of speed. Like just wait for 1 second. So let's discuss about the possible displacement, and before starting it, we are going to discuss an example is related with the speed. Like if we are having some scooters, a set of 6 scooters, and all are moving, then we imposed a restriction that the sum of the speeds of these 6 scooters should be 180 km/h. Now the possible speeds will be 30 kilometer, 30 kilometer, 30, 30, 30, 30. Means all are at the same speed. This is one possibility. One more possibility is there that the speed of the first scooter is 60 km/h, that of second is 20, that of third is 20, that of fourth is 20. And now the rest 2 scooters are at a speed of 30 km/h. Sum is 180. This is also one possibility. One more possibility is there that first 2 scooters are at speed of 45, and then the next 2 are at speed 15 km, and then next 2 are at speed 30 km/h. And these are merely some that we are discussing. There are infinite many possibilities of speed are possible. So when a constraint equation is given, then satisfying that very constraint equation, we are having infinite many possibilities. These are known as the possible velocities. Here, these are the possible speeds. So, for discussing the possible displacement or possible velocity, let's assume on a material system, some finite and differential constraints are imposed. On a system of particles, some conditions are imposed. Out of these conditions, some are and some are. Assume D finite constraints are imposed. Means the number of finite constraints is D. That is F1, F2. So F1 T R1 R2 Rn. Second one is F2 T R1 R2 Rn equal to 0, and last is FD T R1 R2 Rn is equal to 0. Represent these by F alpha TRK is where alpha lies between 1 and D. Okay. After that, assume that on that one there are differential constraints are also imposed. The number of differential constraints is G. So a collection of G constraints, those are differential constraints, are imposed. Okay. Those summation K from Vk plus d beta, where beta varies from 1 to g. Means when beta is 1, first constraint is there. When beta is 2, second constraint is there. When beta is g, gth constraint is there. Okay, so in all, total d constraints are imposed. Out of these d plus g, d constraints are finite and g constraints are differential. Now, solving these d plus g equations, what we did, first differentiate the finite constraints. First we differentiated all the possible finite constraints. So these are the differential constraints. And now differentiating the finite constraints f alpha trk, differentiating that, we will have derivative of f alpha with respect to r1 into derivative of r1, that is r1 dot, then derivative of f alpha with respect to r2 into r2 dot, plus derivative of f alpha with respect to rn and rn dot. So we will have summation k from 1 to capital N, curly f alpha by curly rk vector dot, plus curly f alpha by curly t is equal to from 1 to d. Replacing rk dot by vk, we obtained the equation summation k from 1 to n curly f alpha by curly rk vk plus curly f alpha by curly t dt alpha by curly t is equal to 0. Now we are having d plus g equations which involves v1 v2 vn. How? G differential constraints as for L11 v1 L12 v2 L1 vn plus d equal to 0, Lg1 v1 plus Lg2 v2 plus Lgn plus dg is equal to 0. These are G differential constraints, and D differential constraints obtained due to the finite constraints after differentiating, as in equation number 5. For alpha is equal to 1, first equation, alpha equal to 2, second one, and alpha equal to D, the D equation. So we are having D plus G equations that involves V1, Vn. And now solving these equations for V1, V2, Vn, we obtained the values of V1, V2, Vn, and those very values are known as the possible velocities. The values of V1, V2, Vn that satisfies these D plus G equations are known as possible velocity. Is it okay? Now, next. After that, these are the possible velocities. The values of V1, V2, Vn which satisfies the given D plus G equations. Just a second. I think it is so much increased. So I think possible velocity is clear to you people. Only those values of V1, V2, Vn which satisfies the equations of the given constraints are known as the possible velocities. Now V1, it's the velocity corresponding to the first particle. It will be dr1 by dt, multiplying dt both sides, we will obtain dr1 is equal to 1 dt. Similarly, V2 can be written like dr2 by dt. So dr2 will be equal to V2 dt, and then drn, it will be Vn dt. Now integrating both sides. On left hand side we will obtain r1, r2, rn. On right hand side we will obtain the integration and its value. If we know V1, V2, Vn, that is obtained in the possible velocity section. And with this, corresponding to the possible velocity, we will obtain the possible displacement, because r1, r2, rn are the positions. These are the possible displacements. Hence, corresponding to the possible velocities, we obtained the possible displacements. I am repeating again. A system is given on which some constraints are imposed. The total number of constraints is D plus G. G are finite and G are differential constraints. We differentiated that given finite constraints and obtained the corresponding differential constraints. Now we are having a collection of D plus G equations which involves velocities, means which involves V1, V2, Vn. And the possible values of V1, V2, Vn which satisfies these D plus G equations are known as possible displacements, possible velocities. Now V1 is a velocity, V2 is a velocity, and Vn is a velocity. So V1 will be equal to dr1 by dt, V2 will be equal to dr2 by dt, and Vn will be equal to drn by dt. Multiplying both sides by dt and then integrating, we will obtain r1, r2, rn, and those are known as the possible displacements. So from here we can say that if we know the values of dr1, dr2, drn, then we can obtain the values of r1, r2, rn. Means if dr1, dr2, drn are obtained, then possible displacements can be obtained. So instead of specifying r1, r2, rn as the possible displacements, we are going to mention that dr1, dr2, drn, these are the possible displacements, because with the help of these we can obtain the displacements. Okay. Now after this, let's discuss the virtual displacement. So the equations for possible velocities as obtained earlier are summation k from 1 to n L beta k Vk plus dB, d beta is equal to 0, and summation k from 1 to n f alpha by curly rk V plus curly f curly t is equal to 0. These are the equations for possible velocities. Multiply both sides by dt, then these will become the equations for possible displacements. Next one, virtual displacement. And what is a virtual displacement? Basically, it is the difference between two possible displacements at the same time. The exact possible displacement and the obtained one, the expected one, we can say. Like if we are saying a bike is moving at a speed of 30 km per hour, then we will expect that after 30 minutes, the bike will be at 30 km away from the initial point. But here we ignored the restrictions imposed due to the due to the road. Okay, and in practical, many times we observe that yes, we are moving at a speed of fixed, like at a speed of 10 kilometers, but in 1 hour we are not up to 10 kilometers. We are less a bit. It is due to the constraints present on the road. Some constraints like the air is coming from the front side, then we cannot go up to the marked position. So there are some natural problems that we cannot restrict, that we cannot. So if we are moving 9.9 kilometer, it's the distance in 1 hour. But if I'm talking about that, what will happen in 10 seconds? How much distance will be covered and how much, what is expected and what is actual? The difference between those two is known as the virtual displacement. So here, again, we are having a system with two possible displacements at the same time. Say one is drk and the other is d1rk. Now the equations for possible displacement are, as you know, k from 1 to k drk vector plus d beta dt is equal to 0, and summation curly f alpha by curly rk vector drk vector plus curly f alpha by curly t dt is equal to 0. Replacing drk in this equation and d1rk in these equations, we will obtain the two equations. Like replacing drk, the equation number 11 is obtained, and then d1 rk, then equation number 12 is obtained from the second equation. Similarly, from the first equation, we will obtain two more equations, equation number 13 and 14. Oh, sorry. Yes. Then replacing drk and d prime rk in differential constraint, we will obtain equation. What will happen? We are having equation number 13, 11 and 12. And then 14 from 13, we will obtain summation k from 1 to capital N, L beta k, drk minus d prime rk. Rest terms are cancelled, equal to 0. So we obtained the equation number 15 and 16. Represented by del rk, and now equation number 15 and 16 becomes 18 and 19. Summation k from 1 to capital N curly f alpha by the equation number 18 and 19. Okay, next stage, possible acceleration. I think so. There is an example discussed that some particle is moving on the surface, but the terms are just generalized way. So you can read these. This will help to understand. After that, we are having the degree of freedom. The degree of freedom. To elaborate it, I'm going to again discuss equations from the theory of equations. Like if we are having two equations in three variables, say x minus y plus z is equal to 7 and x plus y plus 2z is equal to 9. And we want to solve these equations, then it is not possible to obtain exact values of x, y and z. Why? Because the number of variables is greater than the number of equations. To obtain values of three variables, we need three independent equations. But this time we are having two equations. To solve this system, we need that one variable should be assumed to be arbitrary. So we replace z k. Such equations, we replaced z by k. And then we obtained the values of x and y in terms of k. Means the values of x and y are dependent on k. So our values were like this: x is equal to 1 plus k, y is equal to 2 minus k, and z is equal to k. This is the solution. Now, what we did one thing, that one variable was assumed to be free from the system. That yes, z is having the value k, and now it's free. It will assume its own values, and according to those values, the values of x and y will be obtained. Okay, so that very coordinate is free from the system, and we will say that the degree of freedom for this system is 1, because one variable is free from the system. This is the degree of freedom. That how many variables are free from the system. Today, what we are to do? We are having d plus g equations. A system of n particles is assumed. Every particle needs 3 coordinates to obtain its positions, because we are representing r1, r2, rn. These are the vector quantities. So r1 will be x1 I cap plus y1 j cap plus z1 k cap. Every vector is having 3 all, a system of n particles means Cartesian coordinate. And plus, so to from the system, the answer is variables number minus minus system can be solved. Okay. After that, we are having the possible acceleration. What is possible acceleration? Basically, all of we know the Newton's second that force equals mass into acceleration. Okay. According to Newton's second law, Fk, the force on kth particle, will be equal to mass of the kth particle mk, and then acceleration, that is represented as omega k, or we can say wk. Now, according to Newton's, yes, this is the exact equation, but this acceleration will not work in the constrained system. Why? Assume we are moving on a bike with a speed of 60 km/h. Some force is generated and that is working okay according to the mass and acceleration. Everything is going okay. But suddenly there is some breaker, a huge breaker. Then to continue the motion, we cannot continue with the speed of 60 km/h. Rather, what we need to apply the brakes, and then we will cover the breaker, we will cross the breaker, and after that, again to continue the motion, we will accelerate it. So what happened? System was moving, force was generated, everything was going well, but suddenly there was some restriction, and due to that restriction, we imposed a force. We applied the brakes. A force is imposed to reduce the speed. That very force that is applied is known as the reaction force. And now after applying that force, now the total force is the actual force that was earlier and the applied force. The sum of these two forces is now your actual force. Means if you are moving on a speed of 60, so the force that was applied to continue that force, that speed, and now to cross the breaker, if we need speed at 10 km/h, so we are to reduce 50 kilometers. So the brakes are applied up to what level? That the speed reduces to 10 kilometers. So the required force, that one. Now the total force applied is the earlier one, the effective one Fk, and the reaction one Rk. This is the total force. And now the motion is continued. After that, we accelerated, some other reaction force is applied. So it was the actual force that was applied. After that, due to the restrictions, we needed some extra force that is represented as Rk. Yes, now the total force is Fk plus Rk. It will be, because now this is the actual force you are. Okay, and then the motion will be continued. So this Rk is known as the reaction force and Fk is the effective force. And in the paragraph, how it was elaborated, it was written like this, that okay, according to Newton's law, Fk will be equal to mk wk. From here we can obtain the value of wk, the acceleration. It will be 1 by mk Fk. But whenever the system is having the restrictions, this acceleration will not work. So to continue the motion, we need extra force that is represented by Rk, and now the actual force is Fk plus Rk, and the obtained from this equation. and this acceleration will be compatible with the given constraint equations. Okay, so this is the actual force yours. Now the next issue is the basic problem. So what is the basic problem? What happens? The system was going on, some force was generated, acceleration we were having, mass is fixed quantity, no issue. Suddenly there were constraints, and to continue the motion we needed some extra force, that is termed as reaction force. But the most important thing, what is the basic problem? Basic problem deals with that how much reaction force is required to continue the motion. For this, I am having an example. Assume a bike is moving with a speed of 90. If there is a breaker, a huge breaker, and we know that to cross this breaker we need the speed to be reduced at 10. So the reaction force should be that enough that is required to reduce the speed from 90 to 10. This is the requirement of the reaction force at that situation. Okay, we reduce the speed at 10 and we cross the breaker and we went. Now the issue is, okay, now we made a mind that okay, whenever there is some restriction, means there is some breaker, the reaction force should be required, and that very reaction force should be like this, that the speed should reduce at up to 80 km/h. Okay, again a breaker came, our speed was 100, we applied the speed brakes and we reduced the speed up to 80 km/h, means now our speed is 20 km/h. But that breaker is merely a small one of height about ½ inch. So I think in this scene there is no requirement of that very reaction force that we required in the previous case. So in every situation the required reaction force is different, and the basic problem is that according to the situation, what is the requirement of the reaction force? Because if the breaker is of ½ inch only, then there is no requirement of reaction force. But it is of 5 inches, then we need reaction force. If it is of 3 inch, then the reaction force will be different. If it is of 2 inches, reaction force will be different. If we are applying the same reaction force in every case, then suddenly in some situations the motion will not continue. If we are saying that okay, we are taking the example of ½ inch and no requirement of reaction force, then in the case when we will obtain the breaker of height 5 inch and no reaction force is applied, then at a speed of 100 km/h we cross the breaker, motion will be discontinued. Okay, so the basic problem of dynamics deals with the problem that how much reaction force is required to continue the motion. Okay, so the next one, ideal constraints. These are those constraints for which the sum of the works of reaction forces over virtual displacements is 0. The work done is force into displacement. Here we are saying that the works of reaction forces over virtual displacements is 0, then the constraints are known as ideal constraints. Means R1 del R1 plus R2 del R2 plus Rn del Rn is equal to 0, or summation k from 1 to n Rk del Rk is equal to 0, then the constraints are known as ideal constraints. In Cartesian form it is explained. R is a force having 3 components, del R is a Rk, it's a displacement vector, so it will have 3 components, and in Cartesian form it is written. Okay, so this is what we discussed up to now. Tomorrow we will try to obtain the Lagrange equation of first kind with the help of all these terms that we have discussed up to now. Okay, I think enough for today. We will discuss the next lecture with some next topic tomorrow. Any problem from your side, you can ask.